is Yang Sun Yao. Now I'm going to do the introduction of blind pendulum. In 1600, Leonardo da Vinci has indicated the very first model of modern clock. His research on the laws of motion influenced him to design the flying pendulum. The flying pendulum clock was invented and patented in 1883 by Edward Christian Clausen and J.Z. Slapter in Minneapolis. The clock was later called the Ignatz Flying Pendulum Clock after a character in the Crazy Cat comic. It has been called the crazy clock in the world due to the motion of the escapement. Next, I will talk about the mechanism and difficulties of the flying pendulum. First, mechanism. A flying pendulum clock is a clock that uses a flying pendulum escapement mechanism. A small metal ball connected by string wraps around one brass post, then unwinds before repeating on the other brass post. Next, difficulties. Unstable spring motion. Because of the mass of coins and the length of rope, each time the swing time may be different. For example, if the length is too long, the rope gets tangled easily. Otherwise, if the mass is too small, then the numbers of turns must be different on two sides.
And next is our math principle part. But before we get to that part, I want to talk about some fun little facts. Because in our project, we use coins to change the mass of the object, so we have to come up with 30 sets of data. These data are basically many combinations of $1, $5, $10, and $50, and we come up with 30 kinds of weight that is possible. And then that's when we measure the time needed in different weights. So now, fun facts. Did you know that 1 NT dollars is 3.8 grams, and 5 NT dollars is 4.4 grams, and 10 NT dollars is 7.5 grams, 50 NT dollars is exactly 10 grams? Did you know that? Well, no, we didn't. We don't either. But now we are very familiar with the weight of these coins. Now, let's start with the actual math part. We divide the motion into 5 parts. The first part is when the object that contains the coins drop to the ground and thus rotate the gear, causing the stick in the middle to rotate the ball attached to the string. But there's a very important part. The length of the string, it doesn't differs, unlike part 2 to part 5. And as for part 2, the string will start to wrap around 2 sticks, one outside and one inside. Part 3 is basically the same as part 2, except that the motion is unwrapping itself from the stick. And as for part 4, the string will only wrap around the stick inside and unwraps itself in part 5. So we observe that the whole system can be divided into 5 parts, and basically part 2 to part 5 is very similar to one another, and the difference between part 1 and other parts only differs in the length of the string. In part 1, the length always stays the same, and for part 2 to 5, the length will get shorter and shorter every time it wraps around the stick.
Part 1 is potential energy transfer into circular motion. When the capital M's drop, the potential energy will decrease and increase the circular motion of this little ball. So we get this equation, which is the potential energy transformed to circular motions. So we get omega is equal to root of this 1, and delta H is the height of potential energy drop. So delta H is Delta H will change according to the number of coins, which is according to the capital M. And we measure of circular motion's radius is equal to 6.5 centimeter. So we can get our period is equal to 2 pi over omega, which is equal to this one. And we will use the change of delta H to get a difference of period. The other part is to calculate our pendulum system. And we assume our pendulum have the small theta, so we can get this formula, which is similar to mass spring vibration. And the mass spring vibrations formula is this one, and we rewrite into this. So we get our discriminators is negative, which is underdamped. So the solution of this equation is combination of cosine and sine. Then we get the period is 2 pi over omega, which is 2 pi times root of m over k. And we get this period solution to our pendulum system. So we look y as theta and k over m as g over l. So our t is equal to 2 pi over root of length over g.
Period of part 2. As you can see, we can describe the period with the formula. 1 second times 2 pi times the square root of L minus A over G plus 1 second times 2 pi times the square root of L minus A minus B over G plus sigma I from 0 to K minus 1 integrate 0 to 2 pi d theta over 2 pi times 2 pi times square root of L minus A minus B minus I times C minus theta times C over 2 pi over G, while K is a round of turns of this part, and A is this part, B is this part, C is this part. In general, the period of a conical pendulum is 2 pi times square root of L over G. For period of part, there are totally 3 parts. First time, the rope wraps around the bar and rotates for 180 degrees. Therefore, the length is L minus A, and we times 1 second to it. Second time, the rope wraps around the bar and also rotates for 180 degrees. And also, we times 1 second to it. For the last part, the rope will wrap around the bar 4k times. Therefore, we do summation from 0 to k minus 1. The formula after sigma is the period of 1 wrap around the bar. Next, for 1 wrap, we cut 1 cycle to multiple intervals. Then for each interval, the length will be L minus A minus B minus I times C minus theta times C over 2 pi. The reason why I times C is subtracted is that at the end of each wrap, the length is subtracted by C. Theta times C over 2 pi is the length decreased at certain degrees. At that, we times d theta over 2 pi to it, which is the proportion of the whole cycle for each interval.
And then we move to the tracker part. The tracker will help us to get the physical data from the video, and this is a user interface we will see. The The first step is to set up the scallop so that we can make sure our measure is right. In the picture, you can see a blue line in the bottom of the picture, and this distance is 40 centimeters. And then we have to set up the coordinates for the video. Then we will use the particle A of the tracker to fix the point we want to check. Then tracker will help us to get the movement of each time and each period. At the right hand side, we can see the graphic and also the data sheet. Next, we will move to the Python simulation.
Hi, I am Denaya Lopete, and I am in charge of the Python simulation for this project. So what we choose to do is to create a linear regression model using Python to determine the influence of the length of the rope and the weight of the coins on the period of the clock. What is linear regression? Linear regression attempts to model the relationship between two variables by fitting a linear equation to the observed data. One variable is considered to be an explanatory variable, and the other is considered to be a dependent variable. Before attempting to fit a linear model to the observed data, we have to make sure that there is a relationship between the variables of interest. A linear regression line has an equation of the form y equals a plus b times x, where x is the explanatory variable and y is the dependent variable. The slope of the line is b and a is the intercept, the value of y when x is 0. Why we choose linear regression? So when we were doing the experiments, after determining how the clock works, we wanted to know if there were any circumstances where the clock period was going to be affected. We started to wonder this because when we are working with a clock, it is supposed to be exact. What I mean is, it has to properly work and tell you the exact time. However, as we knew that the clock mechanism is composed by conical pendulums and circular motion, we knew it can be easy to manipulate the period. We applied linear regression because we wanted to know exactly how is the movement going to be affected by those changes. To construct the linear model, I decided to use two different approaches. One is calculating the linear equation in a self-made function, and also using a predetermined library to verify the results were correct. Now, for the graphics. We divided the linear regression in two parts. The first one that we are seeing now on the screen shows the interaction between the changes in mass. We change the coins from the clock, thus we have different weight moving the clock mechanism. Here we can see that when we increase the weight of the coins, we have a shorter period. And we can also see the linear regression equation on the screen for the relation between these two variables. However, if we only plot the data on the graph, we saw that it was more fitting of an exponential regression because it is looking more like a curve, as in this plot. So we changed the linear regression to exponential regression to analyze the data, coming to this graph. As you can see, it is a curve, and we changed the data points to little hearts because we love ODE. Now, exponential regression refers to the process of arriving at an equation for the exponential curve that best fits a set of data. Now, for the second one, we can see the interaction between the second to the fifth part, the conical pendulum movement. This is the wrapping and unwrapping of the clock. So, what we are seeing is the interaction between these parts and the length of the rope. In this case, the relation we could establish is that when we increase the length of the rope, the period also increases. In this case, you can also see the equation of the slope on the screen. Now, as we stated before, the same happens with this graph. If we only plot the data on the graph, we have something that may look more like a curve. So we did the same thing. We chose to apply the exponential regression, and we also came to this graph where we can see the curve.
This part is our practical realization, and we designed two questions. The first one is, what time does it take when the mass is equal to 30.2 grams and the length is equal to 3 centimeters? From the results in our Python simulation, we get the period is equal to 4.8 seconds, and from our actual observation from tracker, we get the period is equal to 4.5 seconds. So the error is nearly equal to 6.7%.
And the next situation is, how much does the weight of the coins and the length have to be if we want to make the clock run precisely 5 seconds in one round? From our results in our Python simulation, we assume that the length is 4.7 centimeters and the mass is 26.4 grams. And from our actual observation from the tracker, we find that the time needed is 4.912 seconds. So the error is approximately 1.76%. Now let's see the video where we use tracker to capture the time. And for better demonstration, we make this video bigger. So this is the part where it comes from this stick to this stick, and it takes precisely 4.912 seconds, which is very close to our approximation of 5 seconds. Okay, so that's it of our presentation. Thank you for listening.
Thank you.
Now, for the final part, we tried to do some 3D models of the clock on Blender. However, as you can see, we failed. Now, we just incorporate these clips as bloopers because even though we failed, we invested many time on this model. So I hope you can laugh.